Okay, so this is a pendulum. I'm sure you've seen a pendulum before. They come up all over the place. They're in your introductory physics course, they're in your advanced physics courses, and everyone's like, oh, it's a simple pendulum, it's easy. It's not easy, but I'm going to solve this equation, this problem, in a lot of different ways. And let's just get started. Okay, so the number one way is with torque and angular momentum. So if I had to explain this to a student in an introductory course, I think that the angular momentum principle is probably the one that's the clearest and the most straightforward. So let's get started with this. So here I have the mass on the end of a string at some angle, at some position, frozen in time. Well, I know that I have the gravitational force pulling down on the mass. But I also have this tension force in the direction of the string. And so how do you deal with those two situations? It turns out that the angular momentum principle works fairly well. So I need to know a couple things. I need to know the angle. Need to know the length of the string. And I need to know the component of the gravitational force in the direction of the angle, because that's going to be important for the torque. So I need to know that angle right there. Okay, so this is the angular momentum principle. This says that the net torque about some point, any point, but I'm going to pick the point at the pivot point at the top, is equal to the product of the moment of inertia and the angular acceleration. And that's pretty complicated as it is. But if we say that the axis of rotation is fixed, then we can use the moment of inertia as a scalar value. The angular acceleration is fine too. So we need to calculate the torque. We have two forces, so we should have two torques. The first is the torque due to the tension. In general, torque, one way, again, torque is super complicated, but one way to calculate the scalar value of torque is the force times its distance to the pivot point times the sine of the angle between those two. So that's where this RF sine theta comes from. If I do this for the tension, you'll notice that it's a distance L from the pivot point, but the angle between the tension and the distance to that is 180 degrees. It's pi. And the sine of pi is 0. So the torque due to the tension is 0. That's why we use this torque angular momentum principle to model this. Well, there's also the gravitational force, and it has a torque. Now, if I include this direction as positive theta, then the torque from gravity would be in the opposite direction. We'd make it rotate the opposite way. But then we have that mg for the weight, and then L for the distance to the pivot point, and then the angle between those is sine of theta, and we can also represent that as that component theta. So that's my torque. The only torque in the system is negative mg L sine theta. What about the moment of inertia? The moment of inertia is like the rotational mass. It's how hard it is to change its rotational motion, and it depends on the mass and how far that mass is from the point of rotation. So in this case, it's just ml squared. I don't want to give a detailed calculation on how you would get that, but that's what that is. The angular acceleration is just the change in the angular velocity, which is the change in the angular position. So this is actually the second derivative of theta with respect to time, just like linear acceleration is the second time derivative of position with respect to time. So now I can put all this together. So I have the torque, negative mgl sine theta, and is equal to I ml squared times d, the second derivative of theta with respect to time. Now, let me stop for a second. I mean, I went through this fast. I'm going to go through all these things fast. But they're not fast. I mean, don't think that it's super simple. It does take time to really think about these things. And this is the easiest way to present and to calculate the model of a pendulum. Okay, so we have an equation, though. We can, there's an equation, and we can simplify it some. The masses cancel, one of the L's cancel, but I left that out. And now we want to make the first assumption that they always do in introductory physics courses, always do this. They say, well, what if theta is small? If theta is small, then the sine of theta is very close to theta. You can look at that as a sine graph. If you're close to the origin, it looks like a straight line between sine theta and theta. So that's the thing. So theta, sine theta is theta. That's fine. And then the mass cancels, one of the L's cancels, and I get the following expression for the second derivative of the position with respect to time, the angular position, negative g over L times theta. Okay. Now, And again, almost all introductory textbooks do this. They say, look at that. That looks like this. This is the equation for a mass on a spring. So in this case, this is the oscillation of a mass on a spring depends on the spring constant and the mass, and x is the position. That's not the best way to do it, but that's simple harmonic motion. So a pendulum is the same form. It's also simple harmonic motion. That's the idea. So I made this just because I want to show you that it actually is true, and I can make another video about how to make that animation, but I made that in Python. So there's a pendulum, and it has G over L, whatever that may be, and if you pick the right X over M, you can get those two things to move exactly the same. I think that's kind of cool. Maybe you don't think that's cool. I'm cool with you not thinking that's cool, but I think that's cool. So for small theta, a pendulum is simple harmonic motion. Okay, but how do you solve this differential equation? Well, I like to use my favorite differential equation method, which is called guessing. So let's make a guess, because this says that I have some function theta. I take the derivative twice, and it's equal to something times theta. And so what functions do you take the derivative of twice and get the same thing back with a negative sign? And the answer is, one of the answers, there's more than one answer, the answer is, an answer is a trig function. So if I have theta as a function of t is something a times cosine of something times t plus b times sine of something times t, let's just see if that works. So a and omega are constants. So let's take the first derivative. The first derivative of theta with respect to t, well, I have the derivative of cosine is negative sine. But then I have to take the derivative of the inside of omega t, so I get an omega. So I get negative a omega sine omega t. When I do the derivative of sine omega t, I get omega times cosine omega t. So that's where I am. Now I need to take the derivative of this is the second derivative, and I get another omega, and then the other term gets a negative sign. So I get negative a omega squared cosine omega t and negative b omega squared sine omega t. That's just negative omega times theta. It doesn't matter what a and b are. That's what it is. What about, and if I look at the differential equation, then omega would have to be, omega squared would have to be g over L. So omega is the square root of g over L. So that's it. We did it, right? We have an analytical, and we have a function solution to this equation. And you'll notice I put a box around these two things. I put boxes around things that are important. So that's my function. That's my angular velocity, my angular frequency. That's the solution to this differential equation. If theta is small. If theta is not small, then it doesn't work. Okay. Let's do this another way. Okay, so this, we solved it. I didn't plot it, but we solved it. Okay, let's use Newton's second law. So Newton's second law is kind of tricky here, but this says that the net force on an object, the net vector force is equal to mass times acceleration. And acceleration is also a vector. Okay, so if we look at our situation here, we have trouble, and we'll deal with this trouble later. But the trouble is the tension, right? We don't know what the tension is. We can't really calculate the net vector force. So we're going to have to cheat. What we're going to do is to say it's constrained to only move in that path, that circular path. And we call that path the S direction. So that's S, right? So it's a one-dimensional problem. It's not a vector problem. It's only one-dimensional. So I only need the forces in the S direction. So the tension does not exert any forces in the the S direction, because it's perpendicular. But the gravitational force does. And you can see that as the string moves at different angles, the amount of gravitational force in the S direction also changes. So we get this expression, negative mg sine theta, because S is that way, but the gravitational component is in the opposite direction. But we need to deal with this S variable, right? Because I have two variables. I have theta and I have S, where S is the arc length. So if you measure the arc length along that circle, it just depends on the radius of the circle, which happens to be L, and theta. And so you can say S equals L theta. And then if it goes all the way around the circle, then theta would be 2 pi, and you get the circumference. So that's your basic arc length to angle connection. And theta has to be in radians, of course. So what if I want to use Newton's second law, which says F net S is equal to m times acceleration in the s direction, but I want to deal with that in terms of theta. So I need the s acceleration. And so I'm going to introduce some notation, the dot notation. So if I take the derivative of s with respect to t, I'm going to write that as s with a dot over it. This is really common in physics because we think it looks cool, and it does. But more importantly, it saves a lot of space and time. So I can write s dot is the derivative of s with respect to t. And if I take the derivative of s with respect to t, I have to take the derivative of the other side with respect to t. And so the derivative of L theta is going to be L theta dot, right? Because L is a constant, it doesn't change. So if I take the derivative of theta with respect to t, I get theta dot. So S dot is L theta dot. And then I'm going to take the derivative again, and I get S double dot. You see that? It looks really cool. And then it'd just be L theta double dot. Okay, so now I can put that into Newton's second law. This says F net in the S direction is going to be m times the acceleration in the S direction, which is S double dot. And we already showed the component is mg sine theta. Now I have S double dot and I have theta, and I want just one variable. So I'm going to replace the S double dot with L theta dot, and I get mL theta double dot, I meant double, is equal to negative mg sine theta. Divide both sides by ml, and I get the same thing, right? The same thing as before with the angular momentum principle. And I'm going to put a box around that because it's important. Now, what if you don't have a small angle approximation? I'm going to get to that. Okay. So, but I want to point out that the angular momentum, I think, is a more fundamental principle way of doing this. The Newton's second law, you have to use a little trick, right? And I think that is a trick. And honestly, I don't think pendulums are great in the introductory course, unless you're just talking about it in terms of energy or something like that, because it's a complicated problem. Don't fool yourself. Okay, now let's do another solution, and this one I like a lot. Lagrangian Mechanics. If you have, I'm not going to give a full introduction to Lagrangian Mechanics. I do have a video on that. I will link that down below. But let me just say the basic idea of Lagrangian mechanics is that I can define a system based on any variable that I want, in this case in terms of theta, and that I can find out the equations of motion in terms of theta. So here's my pendulum, and it has 1 degree of freedom, right? I only need one thing to tell you exactly where that is, and that 1 degree of freedom is theta. So I don't have to worry about directly x and y. I can just say theta. And that's what makes Lagrangian mechanics so great. So with that, we start off with defining the Lagrangian, which is just the kinetic energy of the system minus the potential energy of the system. With that, the equation of motion can be found from the Euler-Lagrange equation. And so here Q is just some generic variable. It says if I know L in terms of Q and Q dot, where that's the derivative of Q with respect to time, then this equation should be true. This is the idea of the principle of least action, where the action is this path integral of L over time and space, and we want to find the Lagrangian that minimizes that. And so Euler-Lagrange equation minimizes these integrals. So it says that if I take the partial of the Lagrangian with respect to the variable Q, and then subtract the partial of L with respect to Q dot, and then take the derivative of that, it should be equal to 0. So that means that I need to find L, and I need to take the partial, and I'm going to do it in terms of theta, take the partial of L with respect to theta, take the partial of L with respect to theta dot, take the derivative, and then boom. Okay, so, but we do have a problem here, because how do you write kinetic energy in terms of theta dot? It's not trivial. I mean, you could probably guess it, but sometimes later you can't guess it. I can write down the kinetic energy in Cartesian coordinates. It's just 1/2 mass velocity x squared times plus velocity y squared. So x dot squared plus y dot squared. And that's important, right? Because Cartesian coordinates are simple and they're orthogonal and they're easy to write kinetic energy in. And if I can write x and y in terms of theta, then I can find these x dot derivatives and y derivatives and get it in terms of theta. So let's say the origin's at the pivot point, so my y value is going to be negative L cosine theta, my x value is going to be L sine theta, and with that I can go ahead and write the potential. That one's easy, right? It's just mgy based on the with respect to the origin, but y is negative L cosine theta. So I have the potential in terms of theta, so that's good. Now, there's my y equals 0. But now what about, I want to get that kinetic energy. That's my goal. So here's x and y. I already said that. I can take the derivative with respect to time of both of these. So x dot is just going to be, I have to take the derivative of sine theta, and that's going to be cosine theta. But then I have to take the derivative of the inside. It's not a partial. It's a derivative with respect to time. So I have to take the derivative of theta with respect to time. That's theta dot. And I do the same thing for y and get y dot. Remember, the derivative of cosine is negative sine. So I get L theta dot sine theta. Now I can square both these terms and add them together. And it's not too difficult to see that they both have an L squared theta dot squared that factors out, and I get cosine squared plus sine squared, which is 1. So the x dot squared plus y dot squared is L squared theta dot squared. That's pretty nice. So this gives me my kinetic energy, 1/2 mL squared theta dot squared, which does have the same units as real kinetic energy, and you could write this in a lot of different ways. And then my total Lagrangian would be kinetic minus potential. Potential's negative, so I get a plus there. So 1/2 mL squared, and I just realized how dumb I did, but I shouldn't have done this, and I'm sorry. And I'm gonna not change it. I have L for Lagrangian and L for length, and that's pretty stupid. But I think you can see the difference here, and I really feel bad, and I really don't want to change it. So let's just carry on. I should use lowercase l. Why didn't I do that? Or r. Dummy. Okay. And how did I not see that before? If you get really upset and you want me to remake the video, then just tell me down below, and I might do that, but I might not. Okay, so there's my Lagrangian. Now we can use this to plug into the Euler-Lagrange equation and get expressions for theta and theta dot. But you notice the Lagrangian only has theta and theta dot. It doesn't have x's and y's in there. So let's first start with the partial of this with respect to theta. So and this is a partial derivative, right? So everything else is constant, even theta dot. So theta dot's constant. I only need terms that have theta in it, which is the second term. If I take the partial of that with respect to theta, I get negative mgl sine theta. Not too bad. Now let's do the other part, which is the partial of L with respect to theta dot. And again, I assume theta is constant. So it's just a power rule, right? I bring down the 2. I have 2 times 1/2 is 1. And I get ml squared theta dot. Not too bad. Now I need to take the derivative, an actual time derivative of this term with respect to t. And I get, so now I have m, constant, L, constant, theta dot. The derivative of theta dot with respect to time is theta double dot. Now I can put these together. Partial of, that's the Euler-Lagrange equation, partial of L with respect to theta minus the derivative of time of L with respect to theta dot. I get, just putting those two together, I get negative mgl sine theta minus ml theta L squared theta. Double dot is equal to 0. And I can solve for theta dot. No surprise. I get the same thing. Box around it. Okay. So I get the same thing as I've gotten the other 3 ways, which, I mean, come on, it's the same pendulum. I should get the same thing. But how do you solve an equation like this without assuming theta is small? Okay, so let's solve that differential equation. I'm going to use a numerical calculation, and this is the Euler method. Okay, so this is what we're going to do. I'm going to take my differential equation, theta double dot, negative g over L sine theta. And I'm going to pick a short time interval. Let's say delta t is 1/100th of a second. I just picked that. Okay. And short is relative, so it depends on things. during that time interval, it's a short time interval, I can assume that theta double dot is constant. It's not constant, but I can pretend like it is. If I do that, I can define theta double dot as the rate of change of theta dot. And so I can write it like this. Theta double dot is the change in theta dot over the change in time. And then, so here theta 2 dot is the theta dot at the end of the time interval. Theta 1 dot is the theta dot at the beginning of the time interval. If I just solve that equation for theta 2 dot, I get this. So that says take the original theta 1 dot, add theta double dot, which I'm assuming is constant. It's totally not. Multiply it by my time interval, and I get my new theta 2 dot, my new theta dot. Okay. Now I can also assume that theta dot is constant. I know you're thinking, well, you just said it's not. So what? Okay. So there are different numerical recipes. This one actually works fairly well if you do it. And I'm just trying to do something simple. So if I assume theta dot's constant, I can do the same thing with theta dot and theta. So I can define theta dot as the rate of change of theta, and that's theta 2 minus theta 1 over delta t, and I can solve for theta 2. So theta 2 is theta 1 plus theta 2 dot. Now, you do notice that I did something here. Yeah, I used theta 2 dot because I just updated theta dot. So I'm going to use the theta dot I just calculated. So let's put this as a recipe. So number 1, break it into small time steps. Number 2, use the differential equation, theta double dot negative g over L sine theta, and solve for the value, a numerical value for theta double dot. I need a number for that. Use that value of theta double dot to find the new theta dot, just for that short time interval. And then use that theta dot to find the new theta. And then update time, and then repeat it for as long as you want. And that's my numerical calculation of this. Now, this is a numerical calculation. It needs numericals. It needs numbers. I'm not getting an expression. I'm actually just using the numerical values for these things to calculate the future numerical values. I'm getting data, essentially. I need the initial values. I don't need theta double dot, so I can calculate that. But I do need to know what theta is to start with. And I need to know what theta dot is to start with. So that's fine. I mean, if I pull the pendulum off to the side and let go, I could say theta dot is 0 and theta is that initial angle. Okay. But like I said, at the end, you do not get a function. I do not get a sine and cosine function. I get numerical values. I get data, which I can plot, and I can do a lot of stuff with that, but it's still just a number. It's just a set of numbers for the solution, and that's okay. Okay. And it's still legitimate. So here is that numerical calculation, and I'll give you a link to this code down below. Let me just point out some important things over here. This line 2 and 3, it just makes a graph. That's no problem. I have a value for L, and I'm using a scalar value for G. There's my initial theta, and I converted it to radians. Theta dot is my initial angular velocity, and then my time steps. So this line 13, I'm just calculating the differential equation. I'm calculating theta double dot, so you have 2 D's. And then I update theta dot, I update theta, and that's it. That is it. Okay, and I just keep doing it over and over. So this is starting with a 15-degree angle, which is still considered a small angle approximation. And if I plot theta as a function of time, I get this. And that does look like sines and cosines. That agrees with the small angle approximation solution that we had before. But what if I use a large angle? This is for if I do a 45-degree angle, it's not the same thing. It kind of looks like it, but it's not. And you'll notice that actually these don't line up, right? So the periods are different too. So it's not simple harmonic motion. But both of these are done with that same calculation. Okay, so that's Lagrangian. Hamiltonian Mechanics. You may think this one's weird, and I would say, okay, that's kind of fine. And a lot of times people say, oh, well, it's not the best way to do it. But it turns out that Hamiltonian Mechanics turns up a lot of places, quantum mechanics. So the best way to deal with Hamiltonian Mechanics is to start with the Lagrangian. I can already calculate the Lagrangian, so I have this. 1/2 ml squared theta dot squared plus 1/2 plus mgl cosine theta. So we already did that. Now, the Hamiltonian in one dimension is defined as, this looks weird, the Hamiltonian H is p theta. That's the theta momentum, okay? P is momentum, and p theta is the momentum with respect to the theta variable. And I'll get to that. And I'm going to drop the theta on that just a little bit. Times theta dot, the time derivative of theta, minus the Lagrangian. So how do we find p theta? Well, that's just the partial of L with respect to theta dot. And again, you may think this is circular logic stuff, but I'll show you one thing that we do get at the end of this. So if I take the partial of theta of L with respect to theta dot, I get ml squared theta dot. So that is my p theta momentum. And if I put that in, multiply that by theta dot, subtract the Lagrangian, I get this Hamiltonian. So I have ml squared theta dot squared, and then subtract the Lagrangian, and you'll notice that term similar, 1/2 ml squared theta dot squared minus mgl cosine theta. So that's just, I can combine those first two terms as just 1/2 ml squared theta dot squared minus mg cosine L cosine theta. And this is where you say, well, hey, that's kinetic energy, and that's potential. So it's kinetic plus potential. In this case, that is indeed true. That is not always the case. But in this case, the Hamiltonian is the kinetic plus the potential. But I wanted to do it the formal way because, I care. So that gives me this Hamiltonian, which I want to get the Hamiltonian in terms of momentum, P, it's really P theta, and theta. So instead of writing 1/2 ml theta dot L squared theta dot squared, I'm going to use ml squared theta dot. If I square that, I get m squared L to the 4th theta dot squared. But then I need to divide by 2 ml squared to get back to p squared. So p squared over 2 ml squared is the same as the kinetic energy. Okay, so in this case. So now I have the Hamiltonian, I have in terms of p and theta. That's important. And so I'll put a box around it. Put a box around that because it's kind of important. And put a box around this. So now I have the Hamiltonian. I can use Hamilton's equations, not the Hamilton. Okay. So there are two equations that we can use here. One, theta dot is the partial of h with respect to p, and p dot is negative the partial of h with respect to theta. Those are Hamilton's equations. Okay, once you find the Hamilton in terms of p and theta. So there's my Hamiltonian that we said before. So let's take the partial of h with respect to p. So theta dot is the partial of h with respect to p. Well, there's only one p in there. And so I just bring the 2 down, and I get p to the first power. The 2's cancel, so I get p over ml squared. Got that. Okay, now let's find p dot. So p dot is negative the partial of h with respect to theta. So I have a negative. I take the derivative of cosine, I get another negative, and then there's a negative also in the Hamilton equation. So I get negative mg L sine theta. Now, right here, I actually have 2 first-order differential equations, and this is what people would use the Hamiltonian for. The Lagrangian gives you a second-order differential equation because you have the second derivative of theta. Here, I do not have any second derivatives. Okay, so that's why that might make it useful in some cases. But let's show that it's the same thing. So what if I take the derivative of theta dot? So I get theta double dot. So if I take the derivative of theta dot, I take the derivative of p, so it's p dot. So I have p dot over ml squared. But I already know p dot, right? I just have it right there. So if I plug in p dot as that thing, I get this. Theta double dot is going to be the derivative of that. Why did I write that out? I don't know why I wrote that twice. And so I get, but p dot is negative mgl sine theta. If I cancel the masses, if I divide by L squared, I get negative G over L sine theta. And that's the same thing. No one should be surprised. But since we're talking about P and theta, this is where one of the cool things about Hamiltonian, which you can do with other ways too, is to make this phase space diagram. So here are 2 different initial angles at plotting momentum versus theta. And it's a different way to kind of view the motion of the system that gives us some insight into the way things work. I'm not going to go into this in details, but if you talk about the Hamiltonian, normally you talk about phase space just because it's fun. It's fun to say too. Okay, one last way. Newton's second law with springs. So here's the problem. So we have these two forces acting on a mass, and I could use the momentum principle, which is Newton's second law, in most cases the same thing. This says that the total force tells me something about the change in vector momentum. Okay, so I could use this in a numerical calculation. I could solve for, assume the force is constant over a short time interval, solve for the final momentum based on the initial momentum, and I get this, and it's pretty awesome. But I can find the net force, I can find the gravitational force, but I can't find the tension. I don't know the tension force. And you may say, yes, you could figure it out with energy and circular motion and stuff, but I don't know it exactly. I don't know the direction. I don't know a lot of things. I don't know the magnitude, and I don't know the direction. I mean, it's not easy to find that tension force. That string exerts a force of whatever value it needs to keep the thing moving in a circle. So it's not easy. It's a force of constraint, not easy to work with. So let's throw away the string and use a spring instead, because a spring I can calculate the force from. So here's a spring right there on the top, and then I'm going to stretch it. So let's say I have a string and it has an unstretched length L0. And again, I'm using L, and it was a bad idea. You just got to live with your bad ideas. Now if I pull that spring and I stretch it so it has some new vector length, I'm going to write it as a vector so we can deal with directions, a vector length L, and it has a unit vector for the direction L hat, then it's going to exert a force pulling it back in the other direction, Fs. And the spring force is proportional to how much it's stretched. It's not proportional to the length. It's proportional to the difference between the length and the unstretched length. So I can write the following expression for the force due to a spring. Negative, meaning that it's in the direction opposite the way it's stretched. K is a value that tells you the stiffness of the spring, so it's a spring constant, we call that. And then I have to take the stretch, the difference between L and L0, but one's a vector and one's not. So I'm going to write that as the magnitude of L minus L0. That tells me the stretch. But then I don't have a vector force, so I need to multiply by the unit vector L hat to get back as a vector. So that gives me a vector force, and I can move it anywhere I want. I don't have to move in one dimension. That's awesome. It's boxed around that because that's important. Okay, so here's how we're going to do this. So here's my spring instead of a string, and I can calculate that force from the spring if I know the vector length, the unstretched length, and the position, right? I just need to know the position of the mass, and it tells me what direction L hat's in too. So I can calculate the net vector force F net. It's just the spring force plus the gravitational force, and that's equal to the change in momentum with respect to time. And then I can break that into small time steps, and boom, use a numerical program. So here's part of my Python program to solve this. Let me point out a couple things. I had a little problem with the ball moves a little bit with respect to the spring, but it's not a big deal. I could fix it if I want to make it simple more than accurate. So I'm drawing a ball and a spring and stuff. And what I'm doing is calculating this vector position, the vector between the ball and the top point, and that's my L vector. And then I can calculate my total force right there. That's the same equation that we just saw. Oh, wait. No, it is. It is. And then this updates the momentum in line 27, updates the position in line 28, and then just repeats it over and over again. And it actually works pretty well. So here is the same. This is a small angle, and that's a spring. I'm calculating the forces. I'm not modeling it. I'm not calculating theta and then making it move. One of the things that is important here is it's hard to set that initial spring stretch. If you just take a spring, an unstretched spring, and let it swing down, it's going to bounce around, which is cool, but not a pendulum. The best thing to do is put it at the bottom with an initial velocity. And then if I know the velocity, I can calculate how much that spring needs to be stretched to make it move in a circle. And that's what I did here. Okay, so that was 4 ways. So we did the angular momentum principle. I think this is probably the most reasonable approach using introductory physics principles. And then you can use a small angle approximation to show the simple harmonic motion if that's what you want to do. We can, if you want to use Newton's second law in one dimension, you have this problem of the s direction, which is not really one dimension, but that has to introduce these the time derivatives of s and get that in terms of theta, but that works too. Lagrangian mechanics is the way I would do it because it's the best way to define the system, and you could even do something like a double pendulum, a pendulum on the end of a pendulum. If you want to see that derivation, it's not trivial, but it's not impossible. It's pretty much impossible with Newton's second law, though. Hamiltonian mechanics. In this case, you may think it's the same thing as Lagrangian mechanics, and I could say okay, but there are some differences in there, and I wanted to show you the difference in those two. And then finally, springs, not strings. That's just my own way of saying you could replace that force of constraint with an actual spring. And strings are actually stretchy, so it's not a stretch to replace that with a spring. You see what I did there? Okay, so those are actually that's 1, 2, 3. That's 5 ways. Yeah, 5 ways to find the motion of a pendulum. And I'm going to stop there, and that's that.